Welcome to this lesson on polarization. Polarization is a fascinating phenomenon that allows us to control and filter the direction in which light vibrates. Throughout this lesson, we will explore how light can be restricted to vibrate in specific directions and why this property is so important in our everyday lives. To understand polarization, we first need to know what light actually is. Light is an electromagnetic wave, consisting of electric and magnetic fields that oscillate perpendicular to the direction the light travels. This is known as the transverse nature of light. In its natural form, light vibrates in all directions perpendicular to its path of travel. Think of it like ripples spreading out in all directions on a pond. Most natural light sources, like the sun, light bulbs, and candles, produce what we call unpolarized light. In unpolarized light, the electric field vibrations occur randomly in all perpendicular directions with equal probability. There is no preferred orientation. The light waves oscillate up and down, left and right, and in every direction in between, all at the same time. Polarized light is very different. When light becomes polarized, its vibrations are restricted to a single plane. The electric field oscillates in only one specific direction, rather than in all directions. This means we have successfully filtered out all the other directions of vibration, leaving only light that vibrates along one particular axis. A polarizer is a special filter that creates polarized light. It has what we call a transmission axis, which is a specific direction. The polarizer only allows light vibrations that are parallel to this transmission axis to pass through. All vibration components that are perpendicular to the transmission axis get absorbed and blocked. Think of it like a picket fence that only lets waves through if they vibrate in the direction of the gaps between the pickets. When polarized light passes through a second polarizer, called an analyzer, the amount of light that gets through depends on the angle between the two polarizers. This relationship is described by Malus's law. The formula is I equals I naught times cosine squared theta. Here, I is the transmitted intensity, I naught is the initial intensity, and theta is the angle between the polarization direction and the analyzer's axis. When the angle is 0 degrees, all light passes through. When the angle is 90 degrees, no light passes through at all. There are 4 main methods by which light can become polarized. The first is selective absorption, where certain materials absorb light vibrating in specific directions. The second is reflection, where light bouncing off surfaces like water or glass becomes partially polarized. The third is refraction, which occurs when light passes through certain crystals. And the fourth is scattering, which is why the sky appears polarized when you look at it through polarizing sunglasses. Polarization has countless practical applications in our daily lives. Polarizing sunglasses reduce glare from horizontal surfaces like roads and water by blocking horizontally polarized reflected light. Photographers use polarizing filters to enhance colors and reduce unwanted reflections. Liquid crystal displays in our phones, computers, and televisions use polarization to control which pixels appear bright or dark. And three-dimensional cinema technology uses polarization to create the illusion of depth by sending different images to each eye.
If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.